Let yourself settle in for a moment. Find that comfortable position where your body can truly relax, where the weight of the day begins to lift from your shoulders. Take a slow breath, feeling the air move through you, and as you exhale, let any tension drift away like smoke dispersing in the evening air. Tonight, we're going on a journey through the cosmos, but not one that requires any effort from you. Just close your eyes if you'd like, or let them rest gently on a distant point, and allow the story to unfold around you like a gentle tide. We're going to explore something so vast, so incomprehensibly large, that it challenges everything we think we know about size and distance. But don't worry about understanding every detail or remembering every number. Let the words wash over you, painting pictures in your mind of cosmic landscapes that stretch beyond imagination. This is a story about discovery, about the human impulse to look up at the night sky and wonder what lies beyond, and about structures so enormous that they dwarf entire galaxies, the way galaxies dwarf individual stars. So, breathe, relax, and let's drift together into the depths of space, where the biggest galaxy we've ever discovered awaits. The discovery, on an ordinary day in the Netherlands, in a country known more for its windmills and tulip fields than for cosmic revelations, a graduate student named Martijn Ooi was conducting what he thought would be routine analysis of radio telescope data. He wasn't searching for the largest galaxy ever discovered. He wasn't even looking for galaxies at all, really. OAI and his supervisors at Leiden University were investigating something entirely different, examining the distribution of matter in the cosmic web, those invisible threads of gas and dark matter that connect galaxies across the vastness of space. But sometimes, the universe has a way of revealing its secrets when we're looking for something else entirely. The data OA was examining came from a remarkable instrument called LOFAR, which stands for the Low Frequency Array. Picture, if you will, not a single massive telescope dish pointing skyward, but thousands upon thousands of small antennas scattered across the European countryside like a constellation of listening posts. These antennas, about 20,000 of them in total, are distributed across the Netherlands primarily, but they stretch all the way from Ireland to Poland, from Sweden to Bulgaria. Unlike traditional radio telescopes with their enormous moving dishes, LOFAR's antennas stand motionless, simple dipoles that look almost unimpressive individually. But when their signals are combined through sophisticated computer processing, they create one of the most powerful radio observatories on Earth. LOFAR operates in a frequency range that had been largely unexplored before its construction, between 10 and 240 megahertz. These are the same frequencies used by FM radio stations on Earth, but LOFAR uses them to detect some of the faintest whispers from the cosmos. The telescope can peer through dust and gas that would obscure optical telescopes, revealing radio emissions from objects billions of light years away. It's particularly sensitive to the kind of diffuse, extended radio structures that giant radio galaxies produce, structures that had previously been too faint or too spread out for earlier instruments to detect clearly. Martijn Ooi had learned about radio galaxies, of course. Every astronomy student encounters these exotic objects in their studies. He knew that the largest known radio galaxy at the time stretched about 10 million light-years across, already an almost inconceivable distance. But as he processed the LOFAR data, applying new techniques to subtract interfering compact radio sources and enhance the visibility of diffuse structures, something unusual caught his attention. There, in the data, was a radio structure that appeared to stretch much farther than anything he'd seen before. It was a classic configuration. Two enormous lobes of radio emission on opposite sides of a distant galaxy, like wings extending from a cosmic bird. But the scale was unlike anything in the records. Aoi ran the numbers through an online calculator, just to get a rough first estimate. The result made him pause and check his work. According to his calculations, this structure stretched approximately 5 megaparsecs across. For those unfamiliar with the cosmic measuring stick, a megaparsec is roughly 3.26 million light-years. 5 megaparsecs works out to about 16.3 million light-years from one end to the other. OEI, still learning the ropes of radio galaxy research, wasn't entirely sure of the significance of what he was seeing. He sent an email to Martin Hardcastle, one of the world's leading experts on radio galaxies, and a co-author on the study. Hardcastle's response was immediate and unambiguous. Congratulations. This is the largest radio galaxy ever found. The discovery was serendipitous in the truest sense. OE had stumbled upon this cosmic giant not through a systematic search for record-breaking galaxies, but as a byproduct of investigating something entirely different. It's a reminder that in astronomy, as in life, sometimes the most significant discoveries come when we're not specifically looking for them. The universe is full of surprises waiting in the data, hidden in plain sight until the right person with the right tools examines it from the right angle. The galaxy that hosts this stupendous radio structure received the designation SDSS J08142168 Feu Rho, a string of numbers and letters that describes its position in the sky as catalogued by the Sloan Digital Sky Survey. But OA and his colleagues gave it a more memorable name, drawing on Greek mythology, Alcyoneus, after a legendary giant, the king of the Thracian Gigantes, who was said to be immortal within his homeland. The name seemed fitting for a structure of such mythological proportions. Alcyoneus resides in the constellation Lynx, one of the fainter constellations in the northern sky. It's located approximately 3.5 billion light-years from Earth. When the light we're now detecting left Alcyoneus, Earth was a vastly different place. Life was confined to the oceans, and it would be hundreds of millions of years before complex life would emerge on land. The light from this distant galaxy has been traveling through space for more than 3 billion years, crossing incomprehensible distances to reach our telescopes. The discovery paper, published in the journal Astronomy and Astrophysics in 2022, presented not just Alcyoneus, but also revealed that the LOFAR surveys had detected more than 8,000 giant radio galaxies, many of them previously unknown. It was a treasure trove of data, suggesting that these cosmic giants might be more common than astronomers had previously thought. But among all these discoveries, Alcyoneus stood out as the most extreme, the largest structure known to be created by a single galaxy. Understanding scale. To truly appreciate the size of Alcyoneus, we need to embark on a journey through cosmic scales, building up from the familiar to the incomprehensible. Let's start with something we can at least conceptually grasp. The distance light travels in a year. Light moves faster than anything else in the universe, racing through the vacuum of space at approximately 186,000 miles per second. In 1 year, light covers about 5.88 trillion miles, a distance we call a light year. Now, that number alone, 5.88 trillion, is already beyond our everyday experience. If you could somehow travel at the speed of light, which physics tells us is impossible for anything with mass, you could circle the Earth's equator more than 7 times in just 1 second. Yet, even at that incredible speed, it would take you more than 4 years to reach the nearest star system to our Sun. Our home galaxy, the Milky Way, is a majestic spiral of stars, gas, and dust. It contains somewhere between 200 billion and 400 billion stars, each one potentially hosting planets of its own. The Milky Way stretches approximately 100,000 light-years from edge to edge. If you could somehow stand far above the galactic plane and look down, you'd see a beautiful pinwheel structure with graceful spiral arms curving outward from a central bulge. Our Sun sits about 26,000 light-years from the galactic center, in a minor spiral arm called the Orion Spur. To put that in perspective, if you were to board a spacecraft that could travel at the speed of light, a journey from one edge of the Milky Way to the other would take 100,000 years. Civilizations could rise and fall in the time it would take to make that crossing. All of recorded human history, from the first written records in ancient Mesopotamia to the present day, spans only about 5,000 years, a mere 5% of the time it would take light to traverse our galaxy. Now, let's consider our galactic neighborhood. The Milky Way isn't alone in space. It belongs to what astronomers call the Local Group, a collection of more than 50 galaxies bound together by gravity. The largest member of this group is the Andromeda Galaxy, which lies about 2.5 million light-years away from us. On a clear, dark night, far from city lights, you can actually see Andromeda with your naked eyes, a faint smudge of light that's actually the combined glow of 1 trillion stars. In about 4 billion years, the Milky Way and Andromeda will collide and merge, creating a new, larger galaxy that some astronomers have already nicknamed Milkomeda. If we were to line up Milky Ways end to end, it would take 25 of them to span the distance between us and Andromeda. That's the neighborhood scale we're talking about when we discuss the Local Group. These are distances that already strain comprehension, spans of space so vast that the fastest spacecraft humanity has ever built, the New Horizons probe that visited Pluto, would take more than 500 million years to reach Andromeda if it were heading in that direction. But now, let's talk about Alcyonius. This structure, these radiolobes emanating from a single galaxy, stretches approximately 16.3 million light-years across. To put that in terms of Milky Ways, you would need to line up about 163 of our galaxies end to equal the span of Alcyonius. Picture that for a moment. Take the entire Milky Way with its hundreds of billions of stars, all its spiral arms and nebulae and star clusters, and then imagine another 162 galaxies just like it, all lined up in a row. That's the scale we're discussing. Or think about it this way. The distance from Earth to Andromeda, that span of 2.5 million light-years that represents our nearest large galactic neighbor, fits into Alcyonius more than 6 times over. You could place the entire Local Group, our whole galactic neighborhood with all its dozens of galaxies, within the span of Alcyonius with room to spare. Let's try another comparison. Imagine you could somehow shrink yourself down so that you were standing at one edge of Alcyonius, at the tip of one of its radiolobes. You look across to the other side, to the opposite lobe 16.3 million light-years away. If, at that moment, someone on the far side turned on an incredibly powerful lighthouse, bright enough to be visible across that distance, how long would you wait to see its light? The answer is 16.3 million years, when the light finally reached you. Earth would have changed beyond recognition. Species would have evolved and gone extinct. Continents would have shifted. In the time it takes light to cross Alcyonius, entire epochs of life on Earth would have come and gone. Before Alcyonius was discovered, the title of the largest known galaxy was a matter of some debate. Many sources cited IC 1101, a supergiant elliptical galaxy located about 1 billion light-years away in the constellation Virgo. IC 1101 is indeed immense, with a core region spanning about 400,000 to 600,000 light-years, making it 4 to 6 times wider than the Milky Way in its visible stellar component. The galaxy contains approximately 100 trillion stars, 1,000 times more than our own galaxy. At its heart lies one of the largest supermassive black holes ever discovered, with a mass estimated at somewhere between 40 billion and 100 billion times the mass of our Sun. But there's been confusion about IC 1101's actual size. Some sources claimed it stretched as far as 6 million light-years across, but these measurements included its very diffuse halo of stars and the vast cloud of intracluster light, the free-floating stars that have been stripped from galaxies and now wander between galaxies in the Abell 2029 cluster where IC 1101 resides. When astronomers talk about the size of galaxies in terms of their radio emissions, which is what makes Alcyonius so special, IC 1101 doesn't come close to Alcyonius's record. The radio lobes of Alcyonius aren't filled with stars or even much visible matter. Instead, they consist of extremely diffuse plasma, ionized gas that's been accelerated to nearly the speed of light, and then injected into intergalactic space by powerful jets from the galaxy's central supermassive black hole. This plasma glows in radio wavelengths, invisible to our eyes but brilliant when viewed through radio telescopes like LOFAR. The lobes are so diffuse that if you could somehow fly through them, you might encounter only a few particles per cubic meter, making them far more tenuous than the best vacuum we can create in laboratories on Earth. Yet, despite their diffuse nature, these structures are real, they're energetic, and they're enormous. They represent one of the fundamental ways that galaxies interact with and shape their cosmic environment. The energy contained in these lobes is staggering, equivalent to the combined output of trillions of suns over millions of years. This energy didn't come from nowhere. It came from matter falling into the supermassive black hole at the galaxy's center, converted into jets of particles and magnetic fields through processes that represent some of the most extreme physics in the universe. But Alcyonius's reign as the largest structure created by a single galaxy was destined to be short-lived. In September 2024, just over 2 years after Alcyonius's discovery was published, the same team that found Alcyonius announced an even more remarkable discovery. They had found a radio galaxy with jets stretching approximately 7 megaparsecs, or about 23 million light-years across. This new record holder was named Porphyrion, after another giant from Greek mythology, a son of Gaia who rebelled against the gods. Porphyrion's discovery pushed the boundaries even further. It's not just larger than Alcyonius, it's also more distant, located about 7.5 billion light-years from Earth. When we observe Porphyrion, we're seeing it as it existed when the universe was only 6.3 billion years old, less than half its current age of 13.8 billion years. This means that enormous jet systems like Porphyrion have existed for most of cosmic history, reaching across significant fractions of the universe's large-scale structure even in relatively young cosmic times. To match Porphyrion's span, you'd need to line up about 140 Milky Way galaxies end to end. The structure is equivalent to roughly two-thirds the radius of a cosmic void at the epoch when Porphyrion existed. These voids are the enormous empty regions between the cosmic web's filaments, the largest empty spaces in the universe. For a structure created by a single galaxy to reach across such a significant fraction of these cosmic voids suggests that black hole jets may have played a much more important role in shaping the large-scale structure of the universe than astronomers had previously appreciated. The numbers become so large that they lose meaning in conventional terms. When we say 23 million light-years, we're describing a distance that light, traveling at 186,000 miles every single second, takes 23 million years to cross. It's a distance scale on par with the cosmic web itself, the largest known structures in the universe. The nature of radio galaxies. To understand what makes Alcyonius and Porphyrion so remarkable, we need to delve into the nature of radio galaxies themselves. These aren't just large galaxies that happen to emit radio waves. They represent some of the most energetic and dramatic phenomena in the universe. Cosmic engines powered by the most extreme gravitational fields known to exist. At the heart of every radio galaxy, indeed at the center of most large galaxies including our own Milky Way, lies a supermassive black hole. These aren't the stellar mass black holes formed from the collapse of individual massive stars. Supermassive black holes contain millions or even billions of times the mass of our Sun, all concentrated in a region smaller than our solar system. The black hole at the center of the Milky Way, called Sagittarius A Furs, weighs about 4 million solar masses. The black hole powering Alcyonius is estimated at around 400 million solar masses, while Porphyrion's central black hole is thought to be even more massive. A black hole is, at its most basic level, a region of space-time where gravity has become so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. General relativity, Einstein's theory of gravity, predicts that when enough mass becomes concentrated in a small enough region, it will inevitably collapse into a singularity, a point of infinite density where our normal understanding of physics breaks down. Around this singularity, space-time itself is so severely warped that it creates a one-way surface. Anything that crosses the event horizon is doomed to fall inward, eventually reaching the singularity. But black holes aren't just cosmic vacuum cleaners indiscriminately swallowing everything around them. They're actually quite selective eaters. For a black hole to consume material, that material needs to get very close to it. Most of the matter in a galaxy orbits the black hole at safe distances, just as planets orbit the sun without falling into it. However, sometimes gas and dust do fall toward the black hole, perhaps funneled inward by gravitational interactions during a galactic merger, or perhaps just through the normal processes of gas cooling and falling into the gravitational well at the galaxy's center. When matter falls toward a black hole, it doesn't plunge straight in. Instead, due to conservation of angular momentum, it forms a flattened disk of material swirling around the black hole, much like water circling a drain. This structure is called an accretion disk, and it's one of the most violent environments in the universe. As material in the disk spirals inward, it rubs against neighboring material, creating friction. This friction heats the disk to tremendous temperatures, often millions of degrees. The heated disk glows brilliantly across the electromagnetic spectrum, from radio waves to X-rays. Now, Here's where things get truly extraordinary. Not all the material in the accretion disk falls into the black hole. Some of it, perhaps 5 to 10%, gets caught up in the intense magnetic fields that thread through the disk and the spinning spacetime around the black hole itself. These magnetic fields, twisted and amplified by the swirling motion of the charged particles in the disk, act like cosmic particle accelerators and channels. They grab material from the inner regions of the accretion disk and fling it outward in two narrow beams, perpendicular to the disk, along the black hole's rotational axis. These beams, or jets, are among the most powerful and long-lived phenomena in the universe. The material in the jets travels at substantial fractions of the speed of light, often exceeding 99% of light speed. We call them relativistic jets because at these velocities, Einstein's special theory of relativity becomes crucial for understanding their behavior. The exact mechanism by which black holes and their accretion disks produce jets is still not fully understood, and it remains one of the major open questions in astrophysics. Two main theoretical frameworks have been proposed to explain jet formation. The Blandford-Znajek mechanism, proposed in 1977, suggests that the black hole's rotation can be tapped to extract energy. In this model, magnetic field lines threading through the black hole's event horizon can transfer rotational energy from the black hole itself into the jets, like a cosmic generator. The Blandford-Payne mechanism, proposed in 1982, focuses instead on the accretion disk. It suggests that magnetic fields anchored in the disk can extract energy and angular momentum from the disk material and redirect it into jets. In reality, both mechanisms probably contribute to jet formation, with their relative importance depending on factors like the black hole's spin rate and the properties of the accretion disk. The jets don't just shoot out into empty space and disappear. As they travel away from the black hole, they plow into the surrounding environment, the gas that fills the space within and around the galaxy. This interaction creates structure. Near the black hole, the jets are narrow and collimated, tightly focused beams of particles and magnetic fields. As they travel farther out, they begin to spread and slow down, eventually inflating enormous lobes or plumes of radio-emitting plasma. These lobes are what LOFAR detected when it discovered Alcyonius and Porphyrion. The plasma in these lobes consists of electrons and positively charged ions, all moving at high speeds. When these charged particles spiral around magnetic field lines, they emit synchrotron radiation. This process, named after particle accelerators called synchrotrons where it was first observed in laboratories, produces radiation across a broad range of wavelengths. But it's particularly strong at radio frequencies. This is why we call these objects radio galaxies. They're not necessarily producing more total energy than other galaxies, but they're converting a significant fraction of their energy output into radio waves. Radio astronomers classify radio galaxies into different types based on their structure and properties. The most widely used classification system was developed by Bernard Phaneroff and Julia Riley in 1974. They noticed that radio galaxies seem to fall into two distinct classes. Class 1, or FRI, objects are brightest toward their centers. Their jets are easily visible in radio images, but they seem to lose energy as they travel outward, creating diffuse plumes rather than sharp lobes. Class 2, or FRII, objects like Alcyonius and Porphyrion are brightest at their edges. Their jets are often difficult to detect, but they terminate in bright hot spots, where the jet material slams into the surrounding medium. FRI radio galaxies tend to be more powerful than FRI galaxies, and they can maintain their jets over much greater distances. The environment through which these jets travel plays a crucial role in determining how large a radio galaxy can grow. Jets traveling through dense gas will be slowed and disrupted relatively quickly. But jets traveling through thinner environments can extend much farther before their energy is dissipated. This is part of why Alcyonius is such a puzzle. The galaxy itself doesn't appear particularly special. Its stellar mass is actually somewhat below average for giant radio galaxies. Its central black hole, while massive, isn't unusually so. The jets don't appear to be particularly powerful compared to other radio galaxies. So why did Alcyonius grow so large? One possibility is that it simply resides in a less dense region of space, where the intergalactic medium offers less resistance to the jet's expansion. Another possibility is that we're seeing Alcyonius at a particularly favorable angle. If the jets are pointed almost directly along our line of sight, they might appear shorter than they actually are, and we'd be measuring only their projected length on the sky. But detailed analysis suggests that the jets are actually fairly close to perpendicular to our line of sight, so projection effects don't explain Alcyonius's size. Yet another possibility is related to time. Radio galaxies aren't eternal. The jets turn on when the black hole is actively feeding, and they turn off when the fuel supply is interrupted. A typical radio galaxy might remain active for a few 100 million years before the jets shut down. But if the black hole has access to a particularly abundant and steady supply of gas, the jets might remain active for much longer. The longer the jets stay on, the farther they can travel, and the larger the radio lobes can grow. Perhaps Alcyonius simply represents a radio galaxy that has been active for an unusually long time, allowing its lobes to grow to record-breaking sizes. The Cosmic Web Connection. To truly understand the significance of Alcyonius and Porphyrion, we need to zoom out and consider their place in the largest structures known to exist. The Cosmic Web. When astronomers map the distribution of galaxies across the universe, they don't find them scattered randomly like stars. Instead, galaxies are organized into an intricate pattern that resembles a three-dimensional spider's web. There are dense knots where galaxy clusters congregate, containing hundreds or thousands of galaxies bound together by their mutual gravity. From these clusters, long filaments of galaxies stretch out across hundreds of millions of light-years, like threads connecting the knots in a web. Between the filaments lie vast voids, enormous regions that contain few, if any, galaxies, empty bubbles in the cosmic foam that can be hundreds of millions of light-years across. This cosmic web wasn't always so apparent. Through most of the 20th century, astronomers knew that galaxies clumped together in clusters, but they thought these clusters were more or less randomly distributed. The first hints that something more organized was going on came in the 1980s, when astronomers began conducting large-scale surveys that measured the distances to thousands of galaxies. When they plotted those galaxies in 3 dimensions, the web-like pattern became unmistakable. One of the most famous early visualizations of the cosmic web came from a survey conducted by Margaret Geller and John Huchra at Harvard-Smithsonian Center for Astrophysics. In 1989, they published a slice through the universe showing the distribution of galaxies within a wedge of sky extending out to about 600 million light-years. The results were stunning. Galaxies traced out an unmistakable bubble-like structure, with the dense walls surrounding nearly empty voids. One particularly prominent feature, a long curved string of galaxies that Geller and Huchra dubbed the Great Wall, stretched across the survey region like a cosmic, highway. Since then, larger and deeper surveys have mapped the cosmic web in ever greater detail. The Sloan Digital Sky Survey, which began operating in 2000, has measured distances to millions of galaxies, allowing astronomers to map the large-scale structure of the universe out to billions of light-years. The cosmic web is now understood to be one of the fundamental organizing principles of the universe, a structure that encompasses everything from individual galaxies to the largest known structures. But what creates the cosmic web? The answer lies in the universe's history and in the mysterious substance called dark matter. According to our current understanding, the universe began 13.8 billion years ago in the Big Bang, an event that brought space, time, matter, and energy into existence in an unimaginably hot and dense state. In those first moments, the universe was remarkably smooth and uniform, with matter distributed almost evenly throughout space. But not quite evenly. There were tiny variations in density, quantum fluctuations from the earliest instance that had been stretched to cosmic scales by a brief period of exponential expansion called inflation. These tiny density variations, differences of only a few parts per 100,000, were the seeds of all future structure. Regions that were slightly denser than average had slightly stronger gravity, which attracted more matter toward them. As more matter accumulated, their gravity became stronger still, attracting even more matter in a runaway process. Meanwhile, regions that were slightly less dense than average lost matter to the growing dense regions, becoming the voids we see today. But visible matter, the stuff that makes up stars, planets, and people, constitutes only about 15% of the total matter in the universe. The remaining 85% is dark matter, a mysterious substance that doesn't emit, absorb, or reflect light. We know dark matter exists because we can see its gravitational effects on visible matter and on the path of light passing through space. Without dark matter's gravity, galaxies would spin themselves apart. Without dark matter, the cosmic web would look completely different. Dark matter played the dominant role in shaping the cosmic web. Because dark matter doesn't interact with light or with itself through any force except gravity, it could begin clumping together earlier and more efficiently than visible matter. While visible matter was still being buffeted by radiation pressure in the early universe, dark matter was already collecting in dense halos, forming the gravitational scaffolding along which visible matter would later flow. Computer simulations of cosmic structure formation, which track the evolution of millions of dark matter particles through billions of years of cosmic history, beautifully reproduce the web-like structure we observe. The simulations show dark matter collecting along filaments, with the densest concentrations at the intersections where multiple filaments meet. These intersections become galaxy clusters. The filaments themselves act as highways, channels along which gas flows from the voids toward the clusters. This is where radio galaxies like Alcyonius come into the picture. Alcyonius resides in a filament of the cosmic web. Its radio lobes, stretching 16 million light-years, extend through this filament, potentially interacting with the gas that threads through the cosmic web's structure. The jets from Alcyonius aren't just shooting into empty space. They're plowing through the intergalactic medium, the dilute gas that fills the space between galaxies. This intergalactic medium is extraordinarily tenuous. In the voids between filaments, there might be only a few atoms per cubic meter, making it far emptier than the best vacuum we can create in laboratories on Earth. But in the filaments, the density is somewhat higher, perhaps 100 atoms per cubic meter. Over the vast distances these jets travel, even this tenuous gas can have significant effects. As the jets from Alcyonius travel through the intergalactic medium, they're like cosmic snowplows, pushing gas aside and creating bubbles of hot, shocked plasma. This interaction heats the gas to temperatures of millions of degrees, causing it to glow in X-rays. The jets also inject energy and magnetic fields into the intergalactic medium, influencing conditions across enormous volumes of space. This interaction goes both ways. The intergalactic medium also affects the jets. If the jets encounter a region of denser gas, they can be slowed or deflected. If the medium has flows or currents, like winds in Earth's atmosphere, these can bend the jets, creating curved or twisted structures. Some radio galaxies show highly asymmetric lobes, with one side much larger or brighter than the other, possibly because one jet is traveling into a headwind while the other has a tailwind. For Alcyonius, residing in a cosmic web filament means its jets experience a sort of cosmic headwind. Gas in the filament is flowing toward the galaxy cluster at one end of the filament, creating a pressure that the jets must work against. This might actually help explain Alcyonius's enormous size. If the intergalactic medium in this particular filament is unusually tenuous, it would offer less resistance to the jets, allowing them to extend farther before being stopped. The discovery of porphyrion added another layer to this picture. Porphyrion exists in the distant, younger universe, when the cosmic web's structure was still developing. The filaments were closer together, and the voids between them were smaller. For porphyrion's jets to reach 7 megaparsecs in this more compact cosmic web means they extended across an even larger fraction of the universe's structure at that epoch. The jets reached about 2/3 of the way across a void, a truly cosmological scale. This suggests that giant radio galaxies like Alcyonius and Porphyrion aren't just interesting objects in their own right. They're potentially important players in the evolution of the cosmic web itself. The energy they inject into the intergalactic medium can heat gas over vast volumes, preventing it from cooling and condensing to form new galaxies. The magnetic fields they inject can seed the magnetism we detect in galaxy clusters and perhaps even in the filaments themselves. These jets might be one of the primary mechanisms by which the intergalactic medium became magnetized, carrying magnetic fields out from galaxies and distributing them throughout the cosmic web. The mystery of giant growth. One of the most puzzling aspects of Alcyonius is how ordinary the galaxy appears to be, despite producing such an extraordinary structure. When astronomers examine the host galaxy, they find nothing that obviously sets it apart from thousands of other radio galaxies that produce much smaller jets and lobes. The galaxy's stellar mass, the total mass of all its stars, is about 240 billion solar masses. That's substantial, making it more massive than the Milky Way by a factor of 2 or 3. But it's not unusual for a radio galaxy. If anything, it's slightly below average compared to other giant radio galaxies. The galaxy contains mostly old red stars and shows little sign of active star formation. This is typical for large elliptical galaxies, which exhausted most of their star-forming gas billions of years ago, and now shine with the steady light of their aging stellar populations. The supermassive black hole at the galaxy's center has an estimated mass of about 400 million solar masses. Again, this is substantial but not extraordinary. Many radio galaxies harbor black holes of similar or even greater mass. The black hole at the center of the M87 galaxy, famous for being the first black hole ever photographed, weighs about 6.5 billion solar masses, more than 15 times the mass of Alcyonius's black hole. Yet, 87's radio lobes, while impressive, extend only about 250,000 light-years, nowhere near Alcyonius's scale. The jet power of Alcyonius has been estimated at around 10 to the 38th watts. To put that in perspective, that's about 2.5 trillion times the power output of our Sun. It's an almost incomprehensible amount of energy, equivalent to the combined output of millions of galaxies. Yet other radio galaxies produce jets of comparable or even greater power without creating structures anywhere near as large as Alcyonius. So, what makes Alcyonius special? Why did this seemingly ordinary galaxy produce such an extraordinary structure? One leading hypothesis focuses on the environment. Perhaps Alcyonius simply finds itself in an unusually favorable location, a region where the intergalactic medium is particularly sparse. With less gas to push through, the jets could extend farther before their energy dissipates. It's like the difference between running through air versus running through water. The thinner the medium, the farther you can go with the same amount of energy. Evidence supports this idea to some extent. Measurements suggest that Alcyonius does indeed reside in a region where the large-scale environment is somewhat less dense than average. It's not in the dense core of a galaxy cluster, where the hot, dense gas would stifle jet growth. Instead, it appears to be in a quieter cosmic neighborhood, perhaps in the outskirts of a filament where the intergalactic medium is relatively tenuous. But environment alone might not be the whole story. After all, there are plenty of radio galaxies in low-density regions that don't grow to Alcyonius's size. Something else must be at play. Another factor is time. Radio galaxies aren't static objects. They evolve through distinct phases over their lifetimes. When jets first turn on, they're powerful and compact, boring through the surrounding gas and inflating lobes that are initially small but dense and bright. This is the young phase of radio galaxy evolution. As time passes, the jets continue to supply energy to the lobes, and the lobes expand and grow. But they also fade as the relativistic electrons lose energy through synchrotron radiation and other processes. The lifetime of a typical radio galaxy is thought to be somewhere between 10 million and a few 100 million years. This is the period during which the central black hole remains actively fed and the jets stay on. After this, the fuel supply is exhausted or cut off, perhaps because a galaxy merger that provided fresh gas has been completely digested, or because feedback from the jets themselves has pushed away or heated the surrounding gas. When the fuel runs out, the jets turn off, and the radio lobes begin to fade away, their relativistic electrons gradually losing energy until the lobes become invisible even to sensitive radio telescopes. For Alcyonius to grow so large, its jets must have remained active for a very long time. Probably somewhere around 1 billion years. That's much longer than the typical radio galaxy lifetime. It suggests that Alcyonius has had access to an unusually abundant and steady supply of gas feeding its central black hole. Perhaps it experienced a major merger with another galaxy in the distant past, an event that funneled vast amounts of gas toward the central black hole. Or perhaps it's situated at a cosmic crossroads where multiple streams of gas from the cosmic web converge, providing a continuous supply of fuel. there's another intriguing possibility related to the duty cycle of radio galaxy activity. Jets don't necessarily stay on continuously. They can flicker on and off over time, turning on when gas falls toward the black hole and turning off when the fuel is exhausted, only to turn on again later when more gas becomes available. Some radio galaxies show clear evidence of multiple episodes of jet activity, with old, faded lobes from previous episodes, visible alongside bright, compact lobes from a recent reactivation. Could Alcyonius represent a radio galaxy that's gone through multiple cycles of activity, each time extending its lobes a bit farther? This seems unlikely to fully explain its size, because old, faded radio lobes tend to fade away relatively quickly, typically within a few tens of millions of years after the jets shut off. For multiple episodes to contribute to building up Alcyonius's current structure, the gaps between active phases would need to be relatively short, keeping the lobes from fading too much between cycles. But it's possible that Alcyonius represents a particularly favorable case where multiple factors aligned: a low-density environment, multiple feeding episodes, and perhaps just the right timing to allow its lobes to grow to record-breaking sizes. Interestingly, when Ooi and his colleagues analyzed the properties of Alcyonius's jets and lobes in detail, they found that the structure appears relatively young despite its enormous size. The spectral properties of the radio emission, which tell us about the energy distribution of the relativistic electrons, suggest that the lobes have not aged as much as you might expect for such a large structure. This implies that the jets are unusually powerful, or that they've been able to transport energy to the distant lobes particularly efficiently. Another mystery is the asymmetry, or rather the lack of it. Many radio galaxies show significant differences between their two lobes, with one side brighter or more extended than the other. This asymmetry can arise from several factors: differences in the environment on each side of the galaxy, relativistic beaming effects if the jets aren't perpendicular to our line of sight, or intrinsic differences in the power of the two jets. But Alcyonius's lobes are remarkably symmetric. Both sides extend to roughly the same distance, and both have similar brightness and structure. This symmetry suggests that the environment on both sides of the galaxy is remarkably uniform, and that the jets themselves are equally powerful in both directions. The discovery of Porphyrion added new dimensions to these mysteries. Porphyrion is even larger than Alcyonius, yet it exists in the relatively young universe, only 6.3 billion years after the Big Bang. At this epoch, galaxies were more densely packed, galaxy mergers were more common, and the intergalactic medium was somewhat denser on average. How did Porphyrion manage to grow even larger than Alcyonius in these less favorable conditions? One clue comes from the properties of Porphyrion's host galaxy. Like Alcyonius, Porphyrion's host appears to be a fairly ordinary elliptical galaxy, not particularly massive or special. But Porphyrion's environment in the early universe might have offered certain advantages. In the younger cosmos, the cosmic web's filaments were closer together, but they were also more actively growing, with gas flowing along them at higher rates. If Porphyrion's jets happened to align along a filament, they could have traveled along these cosmic highways, following paths of least resistance. Moreover, the early universe had different physical conditions. The cosmic microwave background radiation, the leftover glow from the Big Bang, was more intense in the young universe. This radiation can interact with the relativistic electrons in radio lobes through a process called inverse Compton scattering, providing additional energy losses that cause the lobes to fade more quickly. But it can also provide pressure support, potentially helping to maintain the lobes against the compression from the surrounding intergalactic medium. The balance of these effects in the early universe might have been different from today, perhaps favoring the growth of particularly large structures under the right conditions. The existence of both Alcyonius and Porphyrion suggests that the conditions favoring the growth of giant radio galaxies aren't extremely rare. The LOFAR survey has now identified hundreds of radio galaxies with jets extending beyond several million light years. While Alcyonius and Porphyrion are the extreme cases, they're a part of a broader population. This suggests that the combination of factors needed, the right environment, sufficient black hole feeding, appropriate jet power, occurs often enough that we can find multiple examples even in the relatively limited volume of universe surveyed so far. Porphyrion and beyond. The discovery of Porphyrion in September 2024 represented more than just finding a bigger version of Alcyonius. It opened new windows into understanding the role of black hole jets across cosmic time and their impact on the universe's evolution. Porphyrion, remember, stretches approximately 23 million light-years across, about 40% larger than Alcyonius. But its greater significance lies in its location in spacetime. At 7.5 billion light-years distant, we're observing Porphyrion as it existed when the universe was less than half its current age. This was an epoch sometimes called the adolescent universe, a period when galaxy formation and evolution were still proceeding at a rapid pace, when galaxy mergers were more frequent, and when many of the massive elliptical galaxies we see today were being assembled. Finding such a large radio structure from this epoch tells us that the physical processes capable of creating these giants were already operating efficiently in the relatively young universe. It's not that these structures only developed recently as the universe matured and calmed. Instead, powerful black hole jets were reaching across cosmological distances even when the universe was quite young. The research team that discovered Porphyrion conducted follow-up studies examining the broader implications of such giant jet systems. They found that Porphyrion's jets extended across a region of the cosmic web containing multiple galaxy groups and clusters. At each end of the structure, where the jets terminate, the team detected X-ray emission from hot gas being shocked and heated by the jet impact. This is direct evidence that the jets are actively interacting with and modifying their environment on truly cosmic scales. One of the most significant implications concerns magnetism. The universe's large-scale magnetic fields remain somewhat mysterious in their origins. While small-scale magnetic fields can be generated through various astrophysical processes, explaining how magnetic fields came to thread through the cosmic web's filaments and pervade the space between galaxy clusters has been challenging. Jets from radio galaxies like Porphyrion offer a potential explanation. As jets travel through intergalactic space, they carry magnetic fields with them, frozen into the plasma by the principles of magnetohydrodynamics. These fields can then become entangled with the gas in the cosmic web. When the jets finally shut off and fade, the magnetic fields they carried don't simply disappear. They remain, threading through the intergalactic medium. Over billions of years, as many generations of radio galaxies have turned on and off, these jets could have gradually magnetized vast regions of space. Porphyrion, extending across 23 million light-years in the relatively young universe, demonstrates that this magnetization process has been operating for most of cosmic history. The jets from Porphyrion may have magnetized a volume of space containing dozens or hundreds of galaxy groups, seeding magnetic fields that would later be amplified and organized by turbulent gas motions and structure formation in the cosmic web. The discovery also impacts our understanding of cosmic ray propagation. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that zip through space at nearly the speed of light. While lower-energy cosmic rays come from sources within our galaxy, like supernova remnants, the origin of the highest-energy cosmic rays has been a long-standing mystery. These particles carry so much energy that few astrophysical sources seem capable of producing them. Radio galaxy jets are among the potential sources, as they're known to accelerate particles to extreme energies. If giants like Porphyrion have existed throughout cosmic history, filling huge volumes of the intergalactic medium with relativistic particles and magnetic fields, they could be significant contributors to the highest energy cosmic ray population. The magnetic fields in the lobes could also trap and confine cosmic rays from other sources, creating vast reservoirs of high-energy particles that might eventually escape to contribute to the cosmic ray background we detect. Beyond Porphyrion and Alcyonius, astronomers are now searching for even larger structures. The LOFAR survey that discovered both giants has imaged only a fraction of the sky so far. As the survey continues and as data analysis techniques improve, more giants are almost certain to be discovered. There may well be radio structures out there that stretch 30 million light-years or more, waiting to be found in the data. But there are also theoretical limits to how large these structures can grow. As a jet travels farther from its source, it spreads out and loses energy to its surroundings. Eventually, it reaches a point where it can no longer push forward against the resistance of the intergalactic medium. The energy supplied by the jet gets balanced by the energy lost to synchrotron radiation, inverse Compton scattering, and work done displacing the external gas. At this point, the lobes stop growing, reaching their maximum size. Theoretical calculations suggest that the largest radio galaxies might be able to reach sizes of 30 to 50 million light-years under the most favorable conditions. Beyond this scale, the energy requirements become prohibitive. Even feeding a supermassive black hole at the maximum possible rate couldn't sustain jets powerful enough to reach farther. So, while we might find structures somewhat larger than Porphyrion, there's probably an upper limit somewhere not too far beyond its size. Unless, of course, our understanding of these systems is incomplete. Physics has a way of surprising us. Perhaps there are modes of jet activity we haven't considered, or perhaps the interaction between jets and the cosmic web works differently on the very largest scales. Each new discovery pushes our theories and forces us to refine our understanding. The technical achievements enabling these discoveries deserve mention as well. LOFAR represents a new generation of radio telescope, one that relies on computational power as much as on collecting area. Unlike traditional radio telescopes with their large movable dishes, LOFAR's antennas are stationary. The telescope forms images entirely through computer processing, combining the signals from thousands of individual antennas distributed across Europe. This approach offers unique advantages. LOFAR can observe multiple directions simultaneously, creating maps of large areas of sky in single observations. It's exceptionally sensitive to diffuse, extended emission like the lobes of giant radio galaxies, which would be difficult to detect with traditional interferometers. And it operates at frequencies where Earth's ionosphere becomes highly variable, requiring sophisticated calibration algorithms that astronomers have only recently developed. The Square Kilometre Array, or SKA, now being constructed in Australia and South Africa, will take these capabilities even further. When completed in the late 2020s, SKA will be about 50 times more sensitive than any existing radio telescope and will be able to survey the sky hundreds of times faster than current instruments. With SKA, astronomers expect to find thousands of giant radio galaxies, building up statistically significant samples that will allow them to understand the conditions that favor the growth of these cosmic titans. Future space telescopes will also contribute. The James Webb Space Telescope can observe the host galaxies of distant radio giants in unprecedented detail, revealing their stellar populations and star formation histories. X-ray observatories like the proposed Athena mission could map the hot gas around giant radio galaxies, tracing how jets heat and disperse the intergalactic medium. And gravitational wave observatories might eventually detect the mergers of the supermassive black holes that power these jets, providing entirely new insights into the life cycles of radio galaxies. But we don't need to wait for future facilities to make progress. The archival data from existing surveys contains many more discoveries waiting to be made. The LOFAR data that revealed Alcyonius and Porphyrion covers only about 13% of the northern sky so far. As the survey expands, and as astronomers develop better techniques for identifying and characterizing giant radio galaxies in the data, the census of these objects will grow rapidly. Implications and future. The discovery and study of giant radio galaxies like Alcyonius and Porphyrion have implications that extend far beyond simply cataloging cosmic record holders. These structures are telling us fundamental things about how the universe evolved and how galaxies interact with their surroundings on the largest scales. One of the most important implications concerns galaxy evolution and the phenomenon astronomers call feedback. For decades, theoretical models of how galaxies form and evolve had a significant problem. When astrophysicists simulated galaxy formation using the laws of gravity and gas dynamics, including the processes of gas cooling, star formation, and supernova explosions, their simulations produced galaxies that were too massive and too full of stars compared to the galaxies we actually observe in the universe. The solution to this problem was feedback, mechanisms by which galaxies regulate their own growth. Supernovae, the explosive deaths of massive stars, blast gas out of galaxies, reducing the amount available for future star formation. But supernovae alone couldn't explain the observations, especially for the most massive galaxies. Something else had to be preventing gas from cooling and forming stars in large galaxies. The answer turned out to be the supermassive black holes at galaxies' centers. When these black holes are actively feeding and producing jets, they inject enormous amounts of energy into their surroundings. This energy heats the surrounding gas, preventing it from cooling and condensing to form new stars. In the most massive galaxies, this AGN feedback, where AGN stands for active galactic nucleus, the technical term for an actively feeding supermassive black hole, appears to be the dominant mechanism regulating galaxy growth. But AGN feedback operates on multiple scales. On small scales, jets and winds from the black hole can heat or expel gas from the central regions of the galaxy, directly affecting star formation. On intermediate scales, the jets can create bubbles and cavities in the hot gas that fills galaxy clusters, distributing heat throughout the cluster and preventing cooling flows. Radio observations of nearby clusters routinely show these bubbles, vast cavities carved by jets from the central galaxy's black hole. Giants like Alcyonius and Porphyrion demonstrate that AGN feedback operates on even larger scales than previously appreciated. Jets don't just affect the cluster environment. They reach out into the cosmic web itself, heating gas across millions of light years and potentially influencing galaxy formation throughout entire filaments. The energy injected by these jets may prevent gas in the filaments from cooling and falling into nearby galaxies, reducing the fuel supply for star formation across wide regions. This large-scale feedback could help explain why observed galaxy clusters contain less stellar mass than simulations predict. If jets have been heating the intergalactic medium throughout cosmic history, they may have prevented a significant fraction of the universe's baryonic matter from ever forming stars, leaving it as diffuse gas in the cosmic web. The magnetization story adds another layer of significance. Magnetic fields pervade the universe, but their origin, especially on the largest scales, has been unclear. In galaxies, magnetic fields can be generated through dynamo processes, where the rotation and turbulence of conducting fluids generate and amplify magnetic fields. But in the intergalactic medium, conditions are different. The gas is too diffuse and moves too slowly for dynamo processes to operate efficiently. Jets from radio galaxies offer an alternative mechanism. As they travel through space, jets carry magnetic fields with them, exported from the environment around the supermassive black hole and injected into intergalactic space. When the jets shut off, these magnetic fields remain mixed into the intergalactic gas. Subsequent turbulent motions in the gas, driven by structure formation and galaxy motions, can then amplify these seed fields, building up the large-scale magnetic fields observed in galaxy clusters and potentially throughout the cosmic web. Porphyrion's existence in the young universe, when the cosmic web was still forming, suggests that this seeding process began early in cosmic history. Jets from the first generation of radio galaxies may have provided the initial seed fields that were later amplified to the levels we observe today. This makes radio galaxy jets potentially crucial actors in creating the magnetic universe we inhabit. The implications extend to fundamental cosmology as well. The cosmic web's structure encodes information about the universe's matter content, including dark matter and dark energy. The distribution of galaxies along filaments, the sizes of voids, and the properties of galaxy clusters all depend on cosmological parameters like the matter density, the dark energy equation of state, and the amplitude of initial density fluctuations. If jets from giants like Porphyrion can heat and move gas over tens of millions of light years, they could potentially affect the observable properties of the cosmic web. This needs to be accounted for when using large-scale structure observations to constrain cosmology. Ignoring the effects of AGN feedback on the largest scales could introduce systematic errors into cosmological parameter estimates. Looking forward, several key questions drive ongoing research. How common are giants like Alcyonius and Porphyrion? As surveys cover more of the sky with greater sensitivity, we'll build up statistical samples that will tell us whether these objects represent rare extremes or the tail of a common distribution. Understanding their frequency will help quantify their cumulative impact on the intergalactic medium and cosmic web. What determines which radio galaxies grow to giant sizes? Is it purely a matter of environment and time, or are there intrinsic properties of the host galaxy or black hole that favor giant growth? Detailed studies comparing giant radio galaxies to their smaller cousins might reveal subtle differences that current observations have missed. How efficiently do jets magnetize the intergalactic medium? This requires both observations and simulations. Observations can map the magnetic fields in and around radio galaxies and in the broader cosmic web. Simulations can model how magnetic fields injected by jets spread through space and are amplified by cosmic structure formation. Comparing the two will test whether jets can indeed account for the magnetism we observe. What happens to the relativistic particles in the lobes after the jets shut off? Do they remain confined, gradually losing energy until the lobes fade from view? Or do they escape into the wider intergalactic medium, contributing to a cosmic ray background? And on what timescales do the lobes disperse and mix their material into the surroundings? How do jets interact with the cosmic web at different epochs? Porphyrion existed when the universe was younger and more compact, with different large-scale structure and physical conditions. How did this affect jet propagation and lobe growth? And how have the properties of giant radio galaxies evolved over cosmic time as the universe expanded and its structure evolved? These questions will keep astronomers busy for years to come. Each new survey, each new telescope, each improved simulation adds pieces to the puzzle. The story of radio galaxies connects some of the smallest scales in the universe, the event horizons of black holes, to some of the largest, the filaments of the cosmic web. It's a story that encompasses extreme physics, from quantum effects near black holes to relativistic particle acceleration to the large-scale dynamics of cosmic structure formation. And it's a story that continues to surprise us. Just when astronomers thought they understood radio galaxies reasonably well, along came Alcyonius, revealing that nature can build these structures even larger than expected. Then Porphyrion appeared, pushing the boundaries further still and demonstrating that giants existed even in the universe's youth. Each discovery reminds us that the universe is more extreme, more diverse, and more surprising than our theories anticipate. There's something profoundly humbling about contemplating structures like Alcyonius and Porphyrion. We live on a planet orbiting an ordinary star in the outer regions of an ordinary galaxy. Our entire galaxy, home to hundreds of billions of stars and likely trillions of planets, is dwarfed by these radio structures. All of human history, every empire that rose and fell, every discovery and invention, every work of art and music, all of it takes place on a world that would be invisibly small compared to the scale of Porphyrion's jets. Yet, from this tiny world, we've developed the tools to detect and study these cosmic giants. We've learned to catch the faint whispers of radio waves that have traveled across billions of light years of space. We've developed theories to explain how black holes with masses millions or billions of times that of our Sun can generate jets of particles traveling at nearly the speed of light. We've come to understand that these jets, reaching across millions of light years, play crucial roles in determining how galaxies form, how the intergalactic medium evolves, and how the universe came to be magnetized. The story of radio galaxy discovery is also a story of technological progress and human curiosity. From the first detection of radio emission from space in the 1930s by Karl Jansky, through the development of interferometry and aperture synthesis techniques that allowed radio telescopes to achieve sharp resolution, to modern instruments like LOFAR that combine signals from thousands of antennas using massive computational power. Each step has opened new windows on the universe. And the journey continues. The next generation of instruments will detect giants even more distant, even larger, even more extreme. The Square Kilometer Array will probe radio structures across the entire observable universe. Future low-frequency radio telescopes might operate from the far side of the Moon, shielded from Earth's radio interference, detecting the signature of jets from the universe's first black holes. And, as our understanding deepens, we'll continue to refine our theories of how jets form, how they propagate, and how they influence their cosmic environment. In this way, the discovery of Alcyonius and Porphyrion represents not an ending, but a beginning. These giants have raised new questions even as they've answered old ones. They've revealed that the universe contains structures even more extreme than we imagined, operating on scales that challenge comprehension. And they've shown that there's still so much to learn, so much still hidden in the data from our telescopes, so many discoveries waiting to be made. As you drift toward sleep tonight, you might think about these cosmic giants, these structures so vast that light takes millions of years to cross them. Think about the jets of particles streaming from black holes, traveling at nearly the speed of light across the cosmos. Think about the plasma lobes, glowing in radio wavelengths, marking the extent of a single galaxy's influence across distances that dwarf the spaces between galaxies. And think about the fact that all of this is happening right now, has been happening for billions of years, and will continue for billions more. Somewhere in the universe at this moment, a jet from a newly activated black hole is beginning its journey outward. Somewhere else, an ancient jet is finally shutting down, its black hole having exhausted its fuel supply, leaving behind fading lobes as monuments to millions of years of activity. And everywhere, throughout the cosmic web, the energy and magnetism from countless generations of radio galaxies continue to shape the evolution of structure on the largest scales. These giants remind us that we're part of something vast and ancient, a universe whose depths we're only beginning to explore. They remind us that nature can build structures whose scale defies our everyday intuition, yet whose existence follows from the same physical laws we've discovered by studying phenomena here on Earth. And they remind us that no matter how much we learn, there's always something more to discover, always another surprise waiting in the data, always another mystery ready to challenge our understanding. So, let these thoughts drift through your mind as you relax. Let the numbers and the scales wash over you without worrying about remembering the details. What matters is the sense of awe, the recognition that we live in a universe far stranger and more magnificent than our ancestors could have imagined. What matters is knowing that we've developed the tools and the understanding to detect and study phenomena across the entire observable universe, from quantum fluctuations to cosmic webs. The universe is vast, it's old, it's full of wonders, and somewhere in it, 16.3 million light-years from end to end, stretching across a significant fraction of the cosmic web, lies Alcyonius, and beyond it, 23 million light-years across, reaching through the cosmic web of a younger universe, lies Porphyrion. And perhaps somewhere out there, still undiscovered, lies something even larger, waiting for the next generation of telescopes and the next curious astronomer to find it in the data. These structures exist whether we observe them or not, whether we understand them or not. They've been there for hundreds of millions or billions of years, will remain for hundreds of millions or billions more, long after we and our civilization have passed into history. They're part of the deep structure of reality, cosmic features written into the evolution of the universe by physics and gravity, and the inexorable pull of matter on matter across space and time. And that's a beautiful thought to drift off to sleep with, isn't it? That the universe is filled with wonders on every scale, from the quantum to the cosmic. That we've learned enough to detect and study some of these wonders, even as we recognize how much more remains unknown. That somewhere out in the depths of space, jets are streaming from black holes, galaxies are forming and evolving, and structures of unimaginable size continue their ancient dances. So rest now, knowing that while you sleep, the universe continues its grand performance. Alcyonius continues to shine in radio wavelengths, invisible to human eyes but brilliant to our radio telescopes. Porphyrion, its light having traveled for 7.5 billion years, continues to arrive at our telescopes, bringing information about an epoch when the universe was young. And everywhere, throughout the cosmos, the story of structure formation, of black holes and jets, of feedback and magnetization continues to unfold. Let these cosmic visions carry you gently into sleep. Let the vast scales and long time scales remind you that your immediate worries, while valid and important to you, are small against the backdrop of cosmic time. Find comfort in the vastness, in the knowledge that you are part of this grand cosmic story, a thinking, wondering mind that emerged from stardust to contemplate the structures built by galaxies and black holes across billions of years. The biggest galaxy we've discovered is bigger than imagination. Yes. But imagination itself is perhaps the most remarkable thing of all. The ability of matter organized into brains to conceive of structures millions of light years across, to develop theories explaining their origin, to build instruments capable of detecting them. That's the real wonder. Not just that the universe contains Alcyonius and Porphyrion, but that we, tiny beings on a small world, can discover and understand them. So sleep well, dream of cosmic jets and radio lobes, if you like, or simply let your mind rest. The universe will still be here when you wake, still vast, still ancient, still full of mysteries. And somewhere in it, the search for even larger structures continues, another discovery waiting to surprise us, another reminder that nature's imagination exceeds our own. If you enjoyed this journey through the cosmos, please consider liking this video and subscribing to the Science Pillow. Your support helps me continue creating content that blends education with relaxation, bringing you more stories from the frontiers of science told in a way designed to help you unwind and drift peacefully to sleep. Sweet dreams and clear skies.